This is the problem on the quadriceps, and it says a person is sitting with one leg outstretched so that it makes an angle of 30 degrees with the horizontal, as the drawing indicates. The weight of the leg below the knee is 44.5 newtons, with the center of gravity located below the knee joint. The leg is being held in this position because of the force M applied by the quadriceps muscle, which is attached 0.100 meters below the knee joint. See the drawing, obtain the magnitude of M. So what they're giving to us is the weight of the entire leg, which is 44.5 newtons, or the lower leg actually below the knee. And what they're looking for is the force M that is being exerted by the quadriceps. So this was supposed to be a question mark. And then looks like all the lever arms are given. And then again, it's held in equilibrium. Let's see if the problem actually says that. Actually, the problem itself doesn't say that, kind of like the last problem. However, it said the section title says so. So for all these problems, on the lunch tray, I kind of made an introduction of, whoops, we kind of have to assume that it is in equilibrium, but on second thought, the section header actually says so, rigid objects in equilibrium, and that means all the problems that are being discussed here, the torques come out, the sum of the torques comes out to 0. So I stand corrected for what I said to the last problem about the lunch tray. The title actually says so, and the same thing applies here as well. The problem itself doesn't reveal that, but the header section says that rigid objects in equilibrium, so the torques come out to 0, written as the title. Okay, so let's see what's going to happen here. We have, of course, the weight being pulling down here. Now, on these last problems, it said that we can choose the rotational axis arbitrarily. We could choose it anywhere, here or here or here, but I just want to show that in this case, choosing it here actually, even though that is possible, is very inconvenient, because notice that if we choose the rotational axis here, then the lever arm for the weight comes out to 0, and the only force we have here is mass times that lever arm here. But what is actually the torque that is balancing that? Well, the torque that's balancing it is actually here at the knee joint, where we have probably the muscle in the leg itself holding this one here. However, that force is not given, so therefore choosing this one here arbitrarily, as we're allowed to do, so actually it's not convenient at all, because we do have an unknown, but we don't have any other force given. So therefore I will do it the way they suggest, which is choose the rotational axis at the knee joint, where that unknown force that we don't know here, that is being exerted by the muscle in the upper leg to hold the knee there, doesn't matter that it's not given, because the lever arm is 0 anyway. And now, of course, we have the force M here by the quadriceps. I don't know why they call it M, but they did. And then, of course, here the weight, and this one here produces a counterclockwise torque, while this one here produces a clockwise torque, and the two cancel each other or balance each other. The overall math is not that hard. You'll see that in a couple of minutes or so, but the physics gets kind of interesting, and I want to introduce something here that for some reason our book isn't doing. And they say, you know, use whatever lever arm you have there with the angle, but actually I don't know if the book is really saying that. This is the true definition of torque. That the book says this one here: torque equals lever arm times force. But when you resolved it into scalars, notice that these are vectors, it's torque equals lever arm times force times the sine of the angle, and that sine indicates that the force and the lever arm have to be perpendicular to each other, and you kind of see this in this animation, which is kind of a little bonus in what I'm showing here. So I'm going to write it down as such. Torque equals lever arm times force times the sine of the angle between the two. So torque equals lever arm, or force times lever arm, times the sine of the angle between the two. So that means, okay, maybe I should write this again and make it look a little nicer. Hold on. There, that looks a little nicer. Every time I try to put that little dot there, it kind of smears. Okay, anyway, this here means that when we have this angle, what the actual force is actually that produces torque is this component here, so the sine of that angle, and it's this component of m, which is perpendicular to the lever arm. That makes sense that it's this component here that produces actually the torque, because the parallel, didn't mean to do that, the parallel for the force that is parallel to the lever arm, so the cosine of that angle doesn't produce anything, and actually that's what they do say in the book. I like this better here because that way we can look at the I don't know what to choose here. We can look at it in a little better fashion. So, whoa, that really went off. I meant to draw down the component of gravity that is perpendicular to the lever arm, and that was supposed to be a vector arrow, and then here we would have an angle of course, if this is 30 degrees, then here we have an angle of 60 degrees. So looking at the physics here, the concept itself that's somewhat involved, we have to choose this lever arm times this component of the force, and then add this lever arm here times this component of the force. And again, the torques are equal together, so what I'm going to write down is the mass, I'm sorry, not the mass, the force, capital M, of the quadriceps times that lever arm, LM I guess I call it, times the sine of that angle that it makes, plus the weight of the entire lower leg times the lever arm where the CG is of the lower leg times the sine of that angle where the CG is. The angle with between the weight and the lever arm at that point. And so I'm going to write CG here equals 0. And then what we have here is the only unknown is this m here. And so I'm going to write this as, I need more space I guess, m equals, and then I get, let's see, make a big fraction bar because I'm going to get this one to the right hand side, and then I divide by this stuff here. So I'm going to have negative the weight, I'm just going to plug in the numbers already, so negative 44.5 newtons it was, but that is pointing down already, so I'm going to have negative 44.5 newtons, and again that's smeared, sorry, 4s are kind of tough, they kind of smear into a 9 newtons, times the lever arm on this one here is 0.25 meters, times the sine of the angle between the force and the lever arm itself. Okay, and then actually my fraction bar keeps going on here, and that I divide by the lever arm of the quadriceps, which is 0.100 meters, times the sine of the 25 degrees. Again, it's the angle between the force and the lever arm, and that was already given as such, 25 degrees. And when I plug that in, I come up with 228 newtons. That's a positive number because of those two negatives.